Okay, thanks. Thank you, guys. Okay, so this is what we saw last week. We were basically sort of trying to understand this concept of energy bands. And now we were comparing, right, this parabola where we get an energy continuum. Actually, I don't know what it is. Yeah, this energy continuum, right, versus this concept of energy bands, right? And this is actually how crystals behave. Sorry, how electrons behave in a crystal, right? What we saw last week and what we said last week is actually that electrons, in general, for most k values, for most wave vector values, they actually behave like free electrons. And we see here that this parabola and this set of different energy levels, they sort of superimpose the parabola of the energy continuum, but for certain spaces like this one or like this one. And those spaces are actually when the electron is approaching a multiple of pi over a. So we see that at those values, when the electron is actually around pi over a. So that means when the k value is around pi over a, or a multiple of pi over a, the energy continuum is broken, right? And the electron doesn't behave as a free electron anymore, but it's just around that space, and then it comes back, right? So this is called a periodic zone scheme, and this is, again, this is the thing. This is just representing how electrons behave in crystals. Now there are two other ways to represent this sort of model, right? One is the one in the left, the reduced zone scheme, which what we do basically in that model is just cut the graph between minus pi over a and pi over a. So basically it's like you come here and you just cut, oops, sorry, give me 1 second. It's just like you come and cut there and cut there, and you will get something like this, right? This is actually useful, or a bit more, I guess it just makes things easier to visualize these things that we haven't defined yet, but that's called the energy gap, okay? And these are just the energy bands. For now, we're just gonna call them M band, M band. In later modules, we will give them a name to these bands, a specific name. For now, we're just gonna call them the different electron bands, right? And between bands, we have these gaps, right? These energy gaps. So this just makes things easier. This is nothing new. This is all it's doing is just cutting the plot between minus pi over a and pi over a, nothing else. Now, what about this, right? This is another way of representing, and it's another scheme. It's called the extended zone scheme. This just makes things easier to visualize better, you know, how this continues. So basically, in the extended zone scheme, what they're doing, everything is coming out of this graph, right? This is, as it says here, the periodic zone scheme. Everything is coming out of here. These two zone schemes are coming out of this one, the periodic one. Okay. What's happening in this one, in the extended zone scheme? Well, what's happening there is just that you're sort of deleting the extra things and you just focus. So it's sort of deleting all the waves and you just leave this thing. You're just oops, sorry, let me this. It's basically just plotting this. It's basically, oops, yeah, it's sort of plotting this, right? And well, this can go on and go on, right? So it's just like it takes the important part of that parabola, right? Sort of taking the, you see, and still you get this, right? So you get the important sort of continuum section, and then you get what? The energy the energy gap, and then you continue getting these energy sections, and then here there will be another gap, and then you can keep drawing and drawing this on and on and on, and this will continue, right, with the energy band and the energy gap, and so on, energy band and energy gap. Okay, that's called an extended song scheme. This will go forever and forever if I wish. And this is, I guess, the shortest representation, right? The reduced song scheme. What they're doing is just, I guess, making things easier to visualize. What we're seeing here, that it's just a lot of elements here that it might be difficult to visualize everything here. So these are just two song schemes that are sort of making things easier, and I guess focusing on the important concepts and the important part of the graph. Okay, and then you see something as first BS, second BS, okay? Those are called the Brilliant zones, and that's actually something we're gonna talk in a couple of minutes, but just bear that in your mind, okay? What we see there from minus pi over a to pi over a, that's the first Brilliant zone. And then you see that from pi over a to 2 pi over a, and from minus pi over a to minus 2 pi over a, that's the second Brilliant zone, okay? We're gonna define that concept in a couple of minutes. So something becomes already important here, right? We see that the critical point here, or all the critical points, and that's what basically is represented in these song schemes, is that the critical points are n times pi over a, and n being just a multiple, right? An integer. So n pi over a. So do you guys remember this equation? Or do you remember this equation?
The one on the right, yes, but the left one, yeah, I don't think so.
Okay, the left one is just here. Okay, it just comes out of here, and it's actually here. If you see, it's actually here. It's the same I use here. See, this is just the case or how we started deriving this concept of energy bands. Okay, it's right here. So I'm not coming up with something new. This is something we saw last week, right? So it's just the extended version, I guess. Remember, we defined this extra concept because we defined this periodicity, right? This n2 pi, remember? It was supposed to be only cos of kxa, right? But we remember that cos is periodic every every, I guess, n2 pi, so every 2 pi. And that's why we added that concept, and that's how we came up with this equation, right? So it's nothing new. This is alpha, remember, this coming from alpha. So nothing new, okay? Sorry, that's alpha, okay? So nothing new. You can review that on your own time. So what am I doing here is just solving for E. So you can solve this equation, this whole equation for E. And you can insert different values of n, right? Because n is just supposed to be an integer, right? A multiple that's gonna it's gonna keep defining different critical values of k. So why why am I going to do this, right? Because I can insert different values of n in this equation, right? And I'm going to have the branches or the shape of the branches of the free electron bands. So that just means how the electron bands look like, right? Because I'm solving for energy. Do you remember those plots? And actually all plots we've been doing here, right? All of these plots are energy versus K values, right? I can plot different values of E. Sorry, I can use different values of N, and I'm gonna get the shape of the branches of the free electron bands. So that just means I can solve for E, right? And actually, let's do that. So if N equals 0, right? If I use N equals 0, I'm just gonna use different values of N. And remember that they all have to be integers, right? So if I use N equals 0, what I'm gonna get is just this, right? And well, kx squared, right? Because all this term goes to 0. So how does that look like? It says there, and I guess you can just plot it. That just becomes a parabola, right? This equation is just a parabola with 0 as an origin. If I'm just plotting E versus K, which is what I'm plotting, that's just gonna be a parabola with 0 as an origin. Now let's go with n equal minus 1. So it's going to be the same. I'm just going to have minus 2 pi a. And what is that? Well, that's a parabola with 2 pi over a as an origin. You know, you can get that from math. That's quite easy. And now, so if I do this equation, right, for kx equals 0, I'm going to get that value. And for kx equal pi over a, I'm going to get that value. That's just plugging and inserting the values, because we all know the reduced Planck's constant value. We all know the mass of the electron. Sorry. So there's nothing, I guess, new there. And we will get, and we can keep doing and doing more values of n, and we will get different shapes. So for example, let me use other color now. So if I have, let's say this is value 1, okay, and let's say actually, so for n equals 0, I'm going to get this, right? And we said, well, it's a parabola with n equals 0. Yes, but I'm not going to draw the entire parabola. I'm just going to draw from 0 to pi over a. That's all I'm going to draw. So obviously, it's going to be just that, right? Because remember, pi over a is my critical value, right? And all multiples of pi over a. So I'm going to now use red, and this is going to be for n equal minus 1, and then I get, remember, a parabola with 2 pi over a as an origin. So the origin is here. I can draw this parabola and I can extend it here, but what matters to my plot is this thing, right? Oops, sorry. And I get this, right? And if I were to calculate for n equal 1, for n equals 1, what do you think I'm gonna get for n equals 1, guys? At least what's the shape gonna be? It's gonna be a parabola with what as an origin? Well, it will be a parabola with an origin of minus 2 pi over a. You can calculate that, okay? And you will get this, right? But again, what matters to me is just this part. So all I'm doing is just plugging different values of n in the equation and see how does my energy band looks like. So energy bands. This is an energy band. The M band that you see there, that's an energy band. M band, that is an energy band. So all I'm doing is just see how this looks like. So this is sort of, again, that's a parabola, that's also parabola, that's also parabola. So I'm just showing you where does the shape come from. It's not something trivial. It actually has an equation, right? And I can see, I can keep plotting for n from different values of n. And all I'm doing is just, well, in this case, I'm just plotting from 0 to pi over a. And I'm just seeing how this thing is changing, right? And these are all the different energy values, energy bands possible for this case, okay? So this scheme, if you remember, this, I will call it the reduced sum scheme, because I'm just plotting this part of the graph, right? I'm just using this part from 0 to pi over a, and I'm just plotting that. Now, if you see, there's a difference now, because let me just delete that. If you compare this part, right? If you compare this versus that, you see already a big difference. What's the big difference between that and this?
In the other graph, the terms n are not negative.
Well, I'm not, I mean, it's just a matter of using different values of m, but there is a big difference actually. And I just want you to see the graph. Don't see values, just see the graph. And compare that graph, this graph, to this.
In the first graph, there's no gaps between the terms.
Sorry, I couldn't hear you.
There are no gaps between core.
Yes, in this second graph, there are no gaps between the energy bands. There are no gaps between energy bands. Why? Why do you think is that?
Because there are no critical points. For example, 2 times pi over a, one that
There
multiple.
are. I just that's why I'm using n, right? Those are the critical points. That's why I'm using n. N is 0, it's plus minus 1, it's plus minus 2. Where did I get this equation from? What case was it? You see there? That's the equation. For what case I'm using this equation?
I think it was for the free flying electrons.
Sorry?
Was it for the free flying electrons?
I can't hear you well. Maybe you can type the answer, Nati, or just get closer to your microphone.
Electron in a potential well.
It says there, guys. It's right there. I'm highlighting. Do you see my screen? What I'm highlighting, right?
The
free electrons
electrons.
can move
This
to
free electrons.
negative and the positive side. Can move.
Yes, free electrons. Remember, what happens in free electrons? Energy continuum. No gaps. All possible values of energy are allowed. So this is for energy bands, okay? That's one case, and that's why we got this, because we get energy bands. That's, let's say, the periodic filling a crystal. So remember how electrons actually behave in a crystal, right? But if we just take this case, right, and that's the free electrons case, we get this. We just get an energy continuum. There will be no gaps, and that's the big difference of this case between this case. So if you were to plot the let's say the periodic field in a crystal, so how electrons behave in an actual solid versus free electrons, and remember that what I said is, and that's actually true, electrons actually in a crystal sort of behave like a free electron, and you see that the shape is almost similar, except for what? For the gaps that we have, where? Around pi over a, and all possible, or all integers, or multiples of pi over a. Integer multiples, obviously, of pi over a. So it's just here that in the other case, we get a gap there, and we get a gap here. But everything else is sort of the same, and that's why I'm saying electrons in a crystal behaves like free electrons, except when the wave vector is around the value, the critical value, that in that case is pi over a or multiples of pi over a. What do these graphs actually mean? This E versus K that I've drawn, or well, I've shown you a lot of these E versus K graphs. Well, they're just relating the energy of an electron, because E is energy, remember, to the wave vector. What's the wave vector? It's the momentum, okay? Or it's related to the momentum of the electron. So all they're relating is the energy of the electron versus the momentum of the electron. Okay? So this one, for case of free electron, this one's 4 electrons in a crystal. And this is what we get, why we get these energy bands. Here, yes, we get energy bands, but energy continuum, because all values of energy are allowed. And that's why you don't see discontinuities. That's why you don't see gaps. Here, you do see gaps. Nati said free flying. Yes, Nati. And this is why you get different energy bands and you get energy gaps. Okay, so these are the allowed energy bands. Okay, and then the spaces there, for now, we call them energy gaps, and the other one allowed energies. Okay, or M band. We'll give them a name. I guess in the next module, we'll give them the specific name to these bands. But for now, they're the allowed bands. Questions, guys?
Yes, I have a question.
Yes.
In the last slide,
As well.
no, other. Yes, in this case.
Okay. You can say.
And this case is not similar to.
Sorry,
this case is not similar to the electron potential well, because we have two infinitely high potential barriers, and 0 and P over A, or I'm confused.
Yes, you are confused because there are no potential barriers here. You said you're assuming here you have a potential barrier like this.
Okay.
Sorry, you mean that, right? No, you're
yes.
saying it.
Yeah.
No. The line here, definitely not. The line here not the one I'm overwriting in red. That's just to sort of set the limit, right? But it's not really a barrier here. There's no barrier there. Okay, it doesn't mean that the electron is only moving to pi over a. All I'm doing is just because of this scheme. There are three different schemes. The periodic sum scheme, like this one, where it can keep going forever and forever, right? The reduced sum scheme that I can use to plot just from these values, or even like the one in next slide, just from 0 to pi over a. Why? Because this is periodic, and we're talking about that. All these functions have a periodic factor. So instead of plotting the whole range of k values, I can just plot for one region, and I know that's going to be periodic for the other regions, right? So that's all I'm doing here. It's the graph here. It's not implying that you have a potential barrier here. No, I guess the lines there, they're just limiting the fact that they're saying, I'm just plotting here from 0 to pi over a because that's my sum of interest, because this is going to be periodic. So here, let's say n equal to 0. If I plot it, let's say to minus pi over a, it's going to come in that. But that's periodic. Right? You know, there's symmetry there. That's all this is doing. It's just, and then you can come with the n over 1 with this one. Let me use another color. And the n equal to 1, it's going to come here, right? But you know, the sum I'm plotting there, that's why it's called a reduced sum scheme, because that's the representative one. But then, yes, you can keep plotting this, and this is going to look something like that, I guess. And you can keep plotting for the whole range of k values. Is that clear, Jose?
Yes, of course. It's better to analyze a small section, and because it's periodic.
Yes, that's it. It
It.
doesn't mean so. Yes, so no potential barriers there. Okay.
Thanks.
Okay. So and don't get confused with that, and because also remember, and I guess that's even just to make things clear. Let me get that kind of graphs. Remember, this is B over X. So that's potential energy actually, versus X, versus distance, right? All the graphs we do there are always potential energy versus X, versus distance. Here, it's not V versus X. It's actually energy versus its momentum, okay? It's energy versus momentum. That's another reason to say, don't get confused with potential energies there, because there are no presence of potential energies in that graph. Okay. Okay. Now, I'm just gonna mention something, because this is gonna take us to the next concept that I already mentioned a couple of minutes ago. So this is the same graph, right? Just I guess better looking, but it's sort of the same of this graph, right? And we have again the first allowed band, we have the critical points, okay, and we have the forbidden band on energy gap, and then we have the second allowed band, and then this can keep going and going, remember, as we said, right? Another energy gap, and this will continue, and so on and so on, okay? Now, I just want to stress one more point, because this is going to be important for the next concept. We said that the wave vector is inversely proportional to the wavelength, right? So that means that k, that the wave vector actually has the units of reciprocal length, right? Because if we're talking about the inverse of the wavelength, then k has units of reciprocal length, right? The inverse of length. Therefore, k, so this concept that we've been talking about, the wave vector, it's actually defined in reciprocal space. And I'm sure you've all heard about this concept of reciprocal space, maybe in structure and characterization of materials, or maybe in another class. Have you heard about this concept of reciprocal lattice and reciprocal space, guys? No? Guys, are you there?
I guess we learned that, but I can remember.
Okay.
Yes.
I'm sure you should have learned it in at least structure and characterization of materials, for sure in that course. Not sure if in another course, but for sure in that course, because that's the basis for X-ray diffraction. That's the basis for X-ray diffraction, and you guys learned about X-ray diffraction in that course. So I'm sure you guys learned about that. Anyways, what's a reciprocal or I guess what's the relationship between real space and reciprocal space? For now, we're gonna say that, remember, all cells have different planes, right? So each lattice plane in real space can be represented by a vector that is normal to that plane. So you get the plane, let's say the 1, 0, 0 plane, you get a vector normal to that plane, and the length of that vector must be proportional to the reciprocal of the interplanar distance, so the inverse of the interplane distance. And so with that, so that vector normal to the plane, to the lattice plane, and with length that's the reciprocal of the interplanar distance, you're representing those planes in reciprocal space. Now, what is this concept, or why is this useful, or this concept of reciprocal space? Because that's actually the space. That's, let's say, that's the other reality, if you want to call it, right? We are here in the real world, and then we have to move into that other world, okay? That other dimension, that other space that's called reciprocal space. And that is actually where this K concept, so this concept of wave vector, is defined. If you actually, and I'm sure you can go back to your notes of structure and characterization of materials when you guys took that course. If you remember that pattern, when you see an X-ray diffraction and you get something like that, right? Remember, you get something like that. For if you do an X-ray diffraction pattern, you will get something like that. So all those points there, all those points that you see there, those are actually planes in reciprocal space. So basically, for X-ray, for example, for X-ray diffraction, the pattern is actually a map of a reciprocal lattice. Like you get, let's say, let's say we're actually in 2D. So you get a square as a lattice cell in real space. You can also get those lattices in reciprocal space, right? That's called, it's actually the reciprocal lattice of the structure. So let's say you're analyzing, I don't know, whatever. Let's say you're analyzing hematite, okay, a mineral. When you do an X-ray of that, you will get in the X-ray pattern, you will get basically a map of the reciprocal lattice of that mineral, of the hematite, for example. Okay, so you guys can go back and review that concept, because I'm sure you guys learned it. And why am I sort of mentioning this concept again? because that concept of reciprocal lattice is what allows me to define the wave vector, okay? And that actually allows me to define this concept right here, the Brillouin zone. Let's just look at this graph, and I'm gonna mention already, I'm gonna mention again something that I already did. This part, so from here to here. That's basically the first allowed bands, sorry, the first allowed values of energy, right? And we said that's the first allowed energy band. So from where to where that band goes or extends, that's called the Brillouin zone. And because it's the first one, it's obviously the first Brillouin zone. So if you ask me what the Brillouin zone is, for now I'm going to tell you the Brillouin zone is the values, or well, I guess it's just a set of values of K that define the allowed energy bands. And if we're talking about the first Brillouin zone, well, it's obviously, they're obviously defining the first allowed energy band. So in this case, we'll call it M band. We'll, as I said, in next module, we'll give them another name. And then, so a gap again, so there's a gap here, right? And then it becomes here, right? From here to, sorry, let me use another color and let me do this nicely. So sort of here to here, okay? That's the first Brillouin zone. And it's basically around the same value, because if you see this gap, they're all around minus pi over a, so it's just sort of here as well, right? To here. So this region in yellow, that's now the second Brillouin zone. And you see it has two components, right? It goes from minus pi over a to minus 2 pi over a, and from pi over a, sorry, to 2 pi over a. So it has sort of two components. So the lowest allowed energy band corresponds to the first Brillouin zone. The next higher one corresponds to the second Brillouin zone. The next higher will correspond to the third Brillouin zone. And it will go and on and on and on and on and on, right? Now, if you remember this, right? So we can have different Brillouin zones, right? We have the first Brillouin zone, the second, the third, and we can have infinitely allowed or infinitely Brillouin zones that will define, you know, infinitely allowed energy bands, okay? But to make things easier, actually, we learned that, you know, all these functions or all these concepts have a periodicity, right? They do have a concept of, or they do have a periodic behavior. And in fact, we said that they are 2 pi over a periodic, especially this case, right? The basically this case of the periodic field in a crystal, we say that they're actually 2 pi over a periodic. So if I shift, let's say actually, let's shift this, or I guess this, let's shift all this. So from pi over a to 2 pi over a, shifted by 2 pi over a. Okay, so shifted here. And do the same with this one, right? Do the same with this. Shift this 2 pi over a. And what are you going to get? This will be here, right? Something like that. That will be this one. Let me use another colors actually. So shift this 2 pi over 8 to that side. What you will get be something like this, right? And that will be E, right? So E will be there, and now shift this 2 pi over 8, and you will get that, right? And you can keep doing this, and you will get that. We already saw this graph, right? This is called the reduction scheme. But what's the point here now? Why am I putting this graph again? Because it means that because of this periodicity, I don't need actually to represent all the brilliant zones, because all of them, I can shift them 2 pi over 8 or multiples of 2 pi over 8 and represent everything. So the entire information just in the first brilliant zone. It's just a matter of shifting, right? Just a matter of moving this 2 pi over 8 because that's periodic, and you get this, right? And that's there, that's reflected there, you see. And you can do this so this information is actually, now it's represented in the first brilliant zone, but where did it come from? It comes from the second brilliant zone. So this one right there, from what brilliant zone will become? Sorry, will come, did come. The top one, from what brilliant zone do you think it came? Well, from the third brilliant zone. This is the first brilliant zone, is what you see here, right? This is the second brilliant zone. I'm just shifting because it's periodic in 2 pi over 8. Shifting this, right? Moving this to the left and moving this part to the right. And you get something like that. So now the second brilliant zone is actually represented in the first brilliant zone, because I'm plotting it in this region. So this region is the first brilliant zone. And will be something here, will come something like that, right? It will be something like that, and it will be something like that, right? Actually, no, it's gonna be the other way. Okay, I will have another brilliant zone here, right? Let me plot that. So that's going to be shifted to pi over 8, but anyway, it's going to be something like that, and that's going to be something like that. And then you move it, you shift that, again, multiples of 2 pi over 8, and you get this, right? This shape here. And this information now that should be in the third brilliant zone, because that will be from 2 pi over 8 to 3 pi over 8, right? That is now represented in the first brilliant zone. So my point here is that everything can be represented in the first brilliant zone. Okay? Okay. Now, just to give you this I guess how does a brilliant zone look like now in terms of the reciprocal lattice, because we said this concept actually arises from this idea of reciprocal lattice, right?
Teacher,
Yes.
Natalia has a question in the chat.
Okay. Yes, Nati. Okay, let me check the chat. It says, as we go higher on the B set, the energy bands get wider. Yes. So I guess you mean how? Yes, the width of these bands. Yes, yes, definitely. They get wider. But we'll see that actually it's only these two that matters the most, and we'll see that in the next module. But yes, if you keep going, yes, it will be or the energy bands will get wider, and that's just because if you think of electrons, right? Electrons, the farther from the nucleus, the looser they are, right? The less attracted to the nucleus they are. So yes, that's right. Okay. Thanks. Okay. So let's just I guess see it. I guess more graphical what this beryllium zone concept is. Right? Let's just imagine a two-dimensional lattice. Okay. Let's just sort of imagine that an electron is in a two-dimensional crystal. So just in a two-dimensional lattice, just to understand how this concept is, right? So we know again that the wave vector is basically defining the movement of the electron, right? So the electron can move anywhere in that lattice, right? Just moving in the lattice, just a two-dimensional lattice. And you see that's the lattice there. The point you see there, as I said, that's basically an X-ray diffraction pattern. If anyone, I'm sure you guys learned about that. If you remember, you should have learned about that. And you see those points are different planes, remember, different diffraction patterns, and that's why you get, and that's how you actually can convert that to real space and get what structure that this projection belongs to. Okay, so so basically the wave vector, okay, is gonna define the movement of this electron in X or Y components, right? So basically, all these points that you see there are sort of defining a two-dimensional reciprocal lattice. We're in reciprocal space because we said that K is defining reciprocal space, right? So how do I get these beryllium zones? Well, you just get the vectors that are closest to the origin. And if you see there, those are actually these four, right? And you see there as G1. Let me erase all this. And now there, and there, right? Those are the four closest vectors to the origin, right? Now, let's construct bisectors to these shortest lattice vectors. So these are the shortest lattice vectors we see there, right? If you draw bisectors to those vectors, it will be that, it will be that, it will be that, and it will be that. So there is an area that is enclosed by those bisectors. And it's actually the gray area that you see there, right? So that area, it's the first beryllium zone. It's basically the area that is defined by the bisectors of the shortest lattice vectors. And why the shortest? Because it's the first beryllium zone. Right? So the second beryllium zone will be the second shortest lattice vectors, right? So that means G2, for example. So if I go, that's G, I see only one G2 there. Where's gonna be the other G2? So that's one. The other one will be there. Oops, sorry. The other one will be there, and the will be there, it will be there, right? And you do the same. Draw bisectors to that. If you draw bisectors, where it will be? Well, it will be there. It will be there, and it will be there, and it will be there, and it will be there, right? And so this area is gonna be the second brilliant zone, because it's the area that is enclosed by the bisectors of the second shortest lattice vectors. And you can do the same for the third shortest lattice vectors, and you can do the same for the fourth shortest lattice vectors. And you will get the second and the third brilliant zone. And what's super important here, you will get something like that. There you see, first brilliant zone, this is the first brilliant zone. Second is in gray. So let me actually use, so that's first brilliant zone, that is second brilliant zone, this is third brilliant zone, and this is the fourth brilliant zone. Okay, and you can keep drawing this, drawing, and that those will be the brilliant zones of and you can keep getting the different brilliant zones for this two-dimensional reciprocal lattice, right? But you see something here. Well, you see two things actually. First, the next higher brilliant zone starts or limits with the previous brilliant zone. So if you see actually like here, the second brilliant zone is not or doesn't also include the square there in gray. Doesn't include it. It's what's outside that, and obviously limited by the, in this case, let's say now I'm drawing again the red lines, by the red lines. So if you see the gray area there that corresponds to the second brilliant zone, the gray triangles, they start where the first brilliant zone ends, and obviously they go up to where they actually the bisectors are, right? Where the second brilliant zone is defined. And the same happens with the third brilliant zone and with the fourth brilliant zone. They obviously start, it's not that they sort of enclose all the previous brilliant zones, no. They start where the previous one finished, and then they obviously goes up to where the bisectors sort of enclose the area. And there's another characteristic, if you see the graph, is that all zones have the same area. All zones are equal, right? They all have the same area. So let's say for this one, you have four squares, right? If you, the second brilliant zone, these two triangles will form one square, another square, another square, another square, so the same area. And actually that's something that's always gonna happen. All brilliant zones have the same area. And that's why where you see here, right? We said from here to here is the first brilliant zone. Right? From here to here is the first brilliant zone. Yes, but the second brilliant zone, oh, it's only from here to here. No, because it has another component, that's this one. If you add up these two, they're gonna be equal to this one, to the first brilliant zone. So all brilliant zones have, in this case, the same area. If we're doing a three-dimensional lattice, which actually it should be the way to represent this concept, but I guess just to make things easier, people do this, represent these lattices in 2D instead of 3D. But they have the same area, they will have the same length. If you want to talk about this, if you want to talk about this graph, They have the same length, they have the same area, they have the same volume. If we will be a 3D brilliant zone, maybe we'll do that in a tutorial. So all brilliant zones will have the same value in terms of, you know, area or volume. Okay, questions so far, guys? Nope, nothing in the chat. Okay, I'm gonna stop there for a bit. Stop sharing this. Okay, time for coffee break, guys. Please, I think Giovanni was in charge of the coffee break. So please, Giovanni, while you get ready, I'm gonna do...
Hi.
Hi, Giovanni, please get ready. And while you do that, I'm gonna choose the person for next week. Or actually, I guess 2 weeks from now, because next week we'll have the break holiday. Okay, Julio, you're the chosen person for next week. Are you there, Julio?
Yes, mister.
Yes, okay, Julio. Next week, sorry, I guess 2 weeks from now. 2 announcements, guys. While Giovanni, you can start sharing already, Giovanni. I'm just gonna make 2 announcements. So next week we obviously don't have class because of holidays. So 2 weeks from now there will be a lesson, not a quiz, a lesson. Okay, so we'll have our first lesson 2 weeks from now, and I guess the only lesson from this period. Yes, because I think we have only 2 more, I guess 1 or 2 more classes before the first test. So yes, so 2 weeks from now we'll have you guys will have your first lesson. It's going to be a very short one, and it's actually going to be on Wednesday. It's not going to be on Monday. Okay, so 2 weeks from now, Wednesday, you guys will have your first lesson, and also you guys will have an assignment. I will send the assignment on Wednesday. I will explain the assignment this Wednesday. Okay, so this Wednesday we have a tutorial, so I'll explain there the assignment there, and you guys will have 2 weeks for that assignment, which I guess is a lot of time because it's going to be quite short. But anyways, okay, so just those two announcements. Sorry. Any questions, guys, for this? Okay, no questions, please, Giovanni. Go ahead.
Well, I'm gonna talk about the phase change materials. These materials are materials that can store thermal energy by absorbing heat from their surrounding during the phase change. Then this energy can be released when it's needed. Pcm can be classified according to the type of the phase change which takes place. This can be solid-liquid, solid-solid, and liquid gas. The most common type of the phase change that is used is the solid-liquid, because the other two have some problems. For example, in the liquid gas, the problem is the big difference of the volume of the material when changed to liquid to gas. In the solid-solid, requires a high value for the temperature to let the phase change take place. And the solid liquid has more latent heat value, because so this is preferred because this mechanism is based on the absorb of this latent heat value. However, the Pcm have some problems, general problems, that is the temperature required is higher than the melt temperature, because how as I said, they need to absorb the latent heat volume. So this carries to the lack of control of the energy amount that can be controlled either during the absorb process or releasing process. So this make the PCM have limited applications. The most common applications that are investigated are in smart textile to store solar energy and the heating and cooling loads. Well, there are other materials called the photothermal materials that can transform the light energy into the thermal energy and can be classified as in which material they are based. They can be carbon-based, nanoparticular metal, or organic. This phenomenon occurs by the excitement of electron by the light, which make the electron vibrate, and this conduces to the vibrates of the whole lattice, increasing the temperature of the material. And it's possible to make a composite material using these photothermal materials and the phase change materials. The photothermal material can be used as skeleton or fillet to the phase change materials. Well, the carbon-based PCM can be by carbon nanotubes that have a superior light absorption ability, which means that they will have a good heat transfer, but they also have a good heat transfer ability, and these carbon nanotubes can be used as a skeleton or be inserted in the side of PCM, and a skeleton improves the resistance of the material. Other carbon-based material that can be used is graphene, because it has the higher thermal conductivity from carbon-based materials, even has a higher photothermal performance, and the PCM based with graphene has faster response to the environment change. Then the metal-based PCM, the metal used are nanoparticular, with the phenomena of the local surface plasma resonance. This effect is a collective oscillation of the electron in the metallic interface that takes place by when the frequency of the light is the same of the frequency needed to the electrons vibrate. So this resonance of the all electrons interact with the electromagnetic field, making the free electrons in the metal vibrate. So this carries to the electrons radiate the electromagnetic wave, which increase the temperature of the materials. So, well, this metal-based PCM has faster heating and better thermal conductivity. The most metal nanoparticular used are gold, silver, iron, and well, this PCM composite has the advantage to the normal PCM because normal PCM usually requires very high temperature to absorb and release the energy, no? And for this, for example, they can be used in a cooler regions or in the space, for example. Meanwhile, the photothermal PCM can be used in a disadvantaged environment. Actually, these are studies for intelligence buildings, because this allows to reduce the cost of the energy required for example, heating during the winter or cooling some electronic parts. That's all. Thank you.
Okay, thanks, Giovanni. Questions, guys? I do have a question. It wasn't clear to me what's the difference, or I guess what's the main advantage of a metal PCM versus the other type of PCMs. You were mentioning it, but it wasn't clear to me.
Oh,
can you repeat that, please?
Well, the metal used in PCM are nanoparticulates. So,
yes.
Well, there are also nanoparticles of carbon, but the better performance of PCM in carbon-based materials are when the carbon is a carbon nanotube or graphene. And the properties are similar to the metals, but the metals are a fast velocity to increase his temperature for take place the phase change.
Okay. So at the end, what you're saying is that the main advantage is just they're more efficient in increasing
yes.
the temperature.
We can say that, yes.
Okay. When you were talking about the metals PCM, the matrix is also metallic, and then you have metallic nanoparticles inside the metallic matrix?
No. Actually, these PCM are materials would change their phase to solid liquid, which is the most common used. They can be, for example, farafina in Spanish.
Okay, paraffin, okay.
So really the material can be different. It's not necessary to has to be the same.
What's the common matrix they use? Do you know? Paraffin.
Paraffin are the most are investigating right now.
Okay. Okay. Thank you. Quite interesting topic. Thanks, Giovanni. Okay, let's go. Oh, actually, I already uploaded the slides. Well, I just had to. They were already uploaded. I just had to make it visible to you. So they're already visible. You guys should be able to see the slides of this module, because, well, I don't think we'll finish today. I thought we'll finish today, but anyways, they're already visible, guys. So you guys can go check in Aula Virtual, and if you don't see them, then let me know. But they should be there. Okay. So let's go. Now, so we've been talking about these brilliant zones, and we already said that they're important because they're basically defining where in that reciprocal space our allowed values of energy are, right? Because they're basically relating the wave vector, so basically where the electron is moving, because that's what the wave vector is defining, remember, and that is related to where the allowed values of energies are, right? So we already said that, you know, that brilliant zones are important because of that. And if we want to be specific, we actually can say that the brilliant zones are useful because we can calculate the behavior of an electron. So basically where the electron is moving in that, you know, in any direction in that reciprocal space. So to make it things, I guess, more visible, it's basically where the electron is, oops, sorry, I forgot to use that. Oops. No. Yeah. It is where the electron is moving. It's moving there, it's moving there, it's moving there, it's moving there. Where the electron is moving, right? They actually become useful if you want to calculate, right? How the behavior of that electron is, if it's moving in a specific direction in that reciprocal space. So let's say, for example, right? Let's say the electron is moving or is traveling at 45 degrees to the wave vector x-axis. So the x-axis in this reciprocal space. So if you want to understand, it's basically if the electron is moving there, okay? So it's within the first brilliant zone, right? So if the electron is moving from here to here, how do you get that value, guys?
Maybe with the basic trigonometric
Yes, Pythagoras theorem,
formula.
right?
Yes.
Yes. So remember, all this thing there is K space. So it's reciprocal space, right? And this is just the hypotenuse. So what that will be equal to, let's call it this point here, right? Let me use this point right there. It's called K critical, right? Because we said that it's moving parallel to, it's moving at 45 degrees to the kx axis. So it's moving there, right? So the point right here, this one, up to where it moves, that is called, it's defined as K critical, right? As the critical value, sort of, okay? Well, that's easy, right? You just do trigonometry, so it's pi over a squared plus pi over a squared, right? And the square root of that, right? What's that? Square root of 2 times pi over a, right? That's just trigonometry. You get that, right? Now, if we plug that into the equation that we've had it, right? We get this. That's just plugging in. So that energy, you know, at this value, at this K critical value, that's called the maximal energy or the max energy. What happens at that value? So what happens when the maximal energy is reached? Well, the electron waves form standing waves. What does that mean? The electrons go, reach a wall, they're reflected back into the brilliant zone. So what I'm saying basically is this. The electron is traveling happily, 45 degrees, boom, reaches the first brilliant zone. It's like a wall. Crashes there and it says, "Oop, I have to go back, oops, sorry." And it starts coming back. And so it does this periodically, right? That's what this Emax means. Once the maximal energy has been reached, it's like it's like forming this, right? Forming electron waves, right? But then, boom, it reaches there, and it can keep going like this. It's not gonna keep going. So it's like, oh, I have to go back. So back into the brilliant zone, and it comes back. Right? It comes back, it comes back, and that's why it becomes a standing wave. Right? Because it's not gonna move from there. It's just there. Boom, boom, and it keeps moving there happily and happily. But whenever it reaches the critical value, it will reach the maximal energy, and it will be reflected back into the brilliant zone. It's like reaching the boundary of the brilliant zone. Is that clear, guys?
Teacher, so these standing waves will be present in electrons that are closer to the nucleus of an atom.
Not necessarily. I mean, there are infinitely brilliant zones. There are infinite number of brilliant zones. So basically, you will have them in all electrons. It will be obviously more evident. It might be more evident. Actually, I don't even think so, because yeah, no, it actually belongs to any electron. Yeah.
So how do I get from the first brilliant zone to the second one or to the third one?
Because they are already in the second brilliant zone. The electrons are already present there. You already have electrons in those. And there will be special cases in semiconductors where they can jump from one band to the other. But that's a special case, and we're not going to talk about that yet. We'll talk about that in the next module. But you already have electrons in the brilliant zone. So you already have electrons in the first brilliant zone, and in the second brilliant zone, and in the third brilliant zone.
Okay, so the graph that we were looking at is it's just a plane of the brilliant zone. In reality, it's like a cube or.
Yeah, this is just this one, right?
Yes.
You said it's a plane of a brilliant zone.
No. We are looking at a plane of a solid. I mean, there is also a component.
Well, no. This is actually a two-dimensional reciprocal lattice. This is actually a two-dimensional because I defined that, right? This is a two-dimensional case. So it's just like,
okay.
Let's imagine it's let's say, what's a 2D material? Graphene. Let's imagine this is graphene, right? A 2D material. But actually, there are 3D brilliant zones, and that's actually a bit more complicated, but it's the same concept. So you have planes. And again, you will have you will define bisectors, but in that case will be entire planes that bisect those lattice vectors, and obviously they will at the end form a 3D brilliant volume, right? And you will have brilliant volumes, right? And those will be for solids, for 3D. But just, I guess, for people to understand what this concept of brilliant zone is graphically, it's just easier to represent a 2D lattice. But in reality, you have 3D lattices. And as I said, we might do it one in a tutorial, or maybe I might send it as an assignment to construct a 3D brilliant zone. But it's the same concept. So you do the bisectors, and at the end, all you end up defining is just a 3D solid. And that will be your brilliant zone. So that will be a volume. In this case, it's just a two-dimensional lattice, so that's why you get 2D areas of brilliant zones. Yeah. Is that clear?
Yes. Thanks.
No problem. Okay. Okay. So that's when K is equal to pi a, or square root of 2 pi a. What happens if let's say the electron is moving parallel to kx or parallel to ky. So let's say instead of moving like that, what happens, guys, if the electron is moving like that or like that? What will happen? What's going to be the value of this maximal energy? How is that going to change? Super easy, guys, come on.
Pi over A.
Well, that's pi over a, yeah, that's a critical value. So this equation, this one, what will change in that? Will just be half of that, right? Because you will have a 2 there. This 2 is not going to disappear. This 2 is not going to disappear because now k is only pi over a. So it's basically the maximum energy that the electron can get in that case is just half of the energy that can reach if it moves 45 degrees far to the kx or to the ky axis. It's just a matter of replacing values. I'm not inventing something. That's just maths, guys. So now what's important here? Because at the end, we always want to see what's the relevance of all this, right? What's the relevance of this equation, of this maximum energy? Actually, the concept of that is that you will have overlapping of energy bands in certain materials, and in other materials you will not have that overlapping, and that's what actually makes the difference between metals, insulators, and semiconductors. What's happening? It's this. That's if the electron is moving pi over a. That's the energy, or sorry, the critical value when the electron moves 45 degrees, right? What happens? Look at the energy parabolas, right? If you sort of put this graph on top of this graph, just put it on top, you will see an overlap of values, right? Well, that's actually the difference. This is what happens in metals, for example. Because, yes, it looks like you have energy gaps, because if you see, there are energy gaps. What's the big difference? That in certain cases, like metals, even though I have energy gaps, just look at that, right? It's just, I'm not sure if you guys can see this picture, but I'm just going to extend this so you guys can appreciate that, right? So all values of energy is allowed here, right? And all values of energy is allowed here. Now let's go to the other one. Right? This is just extending there and extending there. So yes, I do have an energy gap there. Yes, I do have an energy gap here. But what's the big difference? In metals, for example, even though I have energy gaps, I have energy bands overlapping. And therefore, if we see overall, there's no energy gap. Overall here, I don't see energy gaps. Yes, I do have different bands. Yes, I do have energy gaps, but for each direction. So electrons moving in different directions, they overlap the different bands. And at the end, overall, I have no gap. Whereas in an insulator or in a semiconductor, and we'll see that in next modules, there is no this overlapping. And therefore, there are actual energy gaps in the whole structure. Is this clear, guys?
With this application of beryllium sounds, we can differentiate these overlapping energy bands of the metals with other materials like ceramics or polymers. This is the meaning of this.
Yes, I mean, the idea of beryllium zones is just defining, because beryllium zones, what they're doing is defining the possible wave vector values that will define the allowed values of energy. And you know that basically electrons are moving within the beryllium zones. Electrons are moving within this. So they're moving within this, they're moving within this, right? And so how that movement happens is different in ceramics, because ceramics, let's say most ceramics are insulators. In metals, because most metals are conductors. So yes, because electrons move in different ways, right? We can have, or we will have in certain materials this behavior, when we have this overlap, like in metals or in conductors. And we'll have another case where there's actually no overlap and there are definite band gaps. So yes, I mean, the idea of beryllium zones, and why I'm talking about this is because they're basically relating, or they're related to the movement of electrons and where electrons are moving. And that at the end ends up defining how what values of energies are allowed, or what energy bands are allowed for different materials. And obviously that implies whether a material is a conductor or an insulator or a semiconductor. Yes. Okay. That's one way, and that's actually the quantum mechanics way of representing beryllium zones. There's an easier way for some people. So the occurrence of critical energies, because remember at the end all this is critical K values, and that defines maximum energies, right? So the occurrence of critical energies at which a reflection of the electron wave takes place, we can use it, basically we can use this concept, we can try to represent this concept in another way, right? So let's consider an electron wave that's propagating in a lattice at an angle theta, right? That angle is parallel to a set of lattice planes. Those incoming rays are diffracted on the lattice atoms at a certain angle of incidence, right? And so you have this. That's basically Bragg's law. Who remembers Bragg's law? So just sort of think of this as a wave of an electron coming in, gets a lattice atom, boom, gets reflected. Right? Just a wave, in this case is an electron wave that's coming into the lattice. It hits a lattice atom and it gets reflected. And that's basically Bragg's law. There will be constructive interference between these different waves. I have wave 1, wave 2, and I can have wave 3, and so on. And there will be constructive interference between these two rays or between these two waves as long as what? What's the condition of Bragg's law? Nobody remembers. Come on. That's Bragg's law. Okay. A is the lattice. Well, remember when I guess when you were learning about Bragg's law, that was actually the interplane distance, the interplanar distance, right? Here, making the analogy, will be the lattice constant, right? So it will be 2a sine theta. It's equal to n times lambda. If you remember, lambda is equal to 2 pi over k, right? So you get that equation. And if you solve for k, you get that equation, right? Now, use this equation. For theta equals 90 degrees, what happens when theta equals 90 degrees?
The sine function is 1.
Yeah, so what do I get? I get m pi over a, right?
Yes.
I get the case of the one I said. I get basically pi over a. So just this. If the electron is moving, sorry, it's moving either there, is moving either there or there. Now, use 45 degrees. What happens if theta equals 45 degrees?
The sine is we have the maximum energy with critical K.
We'll have this value of k, square root of 2 pi a, okay, which is the same. So 45 degrees, 45 degrees. For 45 degrees, what did we get? This equation. You get this, you get the same value. So just another way of getting these k critical values and obviously the maximal energies that the electrons can reach. It's just another way of finding, I guess, the values. Just and for some people, it's this way. It's easier. I guess it really depends. Okay. And at the end, it's the same concept, right? When you get the critical value of k, the transmission of the electron beam through the lattice is prevented. There is no transmission. There is reflection. Right? When you get the critical value, there's no transmission. There's reflection. There's reflection. Sorry. And then you get the same idea. You get the standing wave. So here and here, you get reflected. Oops, and then again and again, and you get a standing wave. Right? It's the same concept. Okay. Time to get into more complicated stuff. All we've been talking about is energy bands, right? Well, this whole idea of energy bands, if we just put all the energy bands in one graph, we'll get energy. We'll get, sorry, band structures, right? Like this. There you see a graph of a band structure. So basically different bands, right? The graph is basically the same. You're plotting energy. In the x axis, you see something weird. You see some letters that are a bit weird, and they might look a bit weird, but they're basically reciprocal space. Okay? It's just that, for example, I can tell you this minus, I believe, minus x. Yes, so this part, right? Sorry, that part. That represents the 1, 0, 0 direction in reciprocal space, for example, right? That's just a notation they use, okay? I don't want to get into that so deep, okay? But let's say, for example, this will represent what's happening in the 1, 0, 0 direction in K space, so in reciprocal space, right? And you can see other directions here. You see also, for example, this minus, oops, sorry, this minus K. That's actually, for example, the 1, 1, 0. Okay, so you're basically seeing different directions in K space, in reciprocal space. So at the end is the same graph, right? Energy versus K, right? Versus the reciprocal space versus the momentum of the electron. So the same thing. So now what you see, you see a much more complicated graph, right? You see that, and you see what's that? It looks much more complicated, right? But at the end, it's the same graph. It's just that it's defined, or it's sort of sectioned for different directions in K space, right? But at the end, it's basically the same. And how you define those directions? Well, it's with this, right? Say you're finding K critical, and you're defining for this, for example. You're finding, let's say, if the electron is moving in pi over a, if the electron is moving in pi over a square root of 2, so if it's moving at 45 degrees, if it's moving at 0 degrees, at, let's say, I don't know, 30 degrees, and that's all defined because of the directions, right? Whether it's the 1, 0, 0, and combined with the 1, 1, 0, the 1, 1, 1, whatever, right? So I'm not going to get into detail because it's just a matter of showing you what the idea of this graph is. So you can actually calculate that, and obviously people do that in a computer because by hand that's quite complicated. But actually, yes, so you can use all these equations that you see here, right, for different directions. Use this K value and this energy value, right? Yeah, this energy equation, right? To plot this, and you'll get something like this, for different directions. As it says, this is all calculations, computer-rated calculations, right? And investigators use different starting potentials and potential energies and everything. You use the Schrödinger equation, okay, and boom, plot that, and you get something like this, right? And yes, it's a bit complicated, but this is actually quite important. Remember that this is all calculations, right? You can't really measure this. This is all calculations. And there are certain things, for example, you can measure the frequency dependence of the optical properties. So you can change frequency and see how optical properties change or don't change as I'm changing frequency. And then that will sort of help me to see, okay, so this band structure is sort of close to reality. Let's say I can align it, let's say in the 110 or maybe in the 111 direction and say, oh, it did change or it didn't change. And then I see, oh yeah, these calculations are correct or incorrect, or they're sort of close to reality or not close to reality, right? But at the end, you can't really measure this. All these graphs are all calculated. They're not experimental at all. They're all computer-aided calculations with the equations I've shown you so far. Okay? And you get this graph. This is a band structure. So this is the whole, or I guess the main band structure of a material. And actually, can anyone guess what material you guys are looking at? now. What material does this graph, this band structure, belong to? So this, the only thing that this is changing is that this is representing for more directions. Yeah. The graphs here, these graphs, for example, this is only for one direction. This is for one direction, right? This is for one direction. Okay. The only thing that's changing is the same graph, but now it's represented for more directions, for more k directions, but at the end it's the same graph. So what material you guys think this band structure belong to? What element?
Maybe a metal because there is no gaps, energy gaps, and which element? I don't know.
Yeah, well, that's difficult, but yes, it's a metal. Perfect.
Maybe silver.
It's aluminum.
Okay.
The material you're looking at is aluminum. And it's what I was saying before. Yes, there are energy gaps. Yes, right there. Right there, energy gaps. Right there, energy gaps. But overall, you see in different directions. That's for one direction, for another, for another, for another, for another direction. Overall, as Miguel said, there are no band gaps. Yes, I do have band gaps there, but in other directions, I have values of energy. Like for example, here in that range, for this direction, I have allowed values of energy. So overall, if I see that graph, yes, specifically there are band gaps or energy gaps, but overall, you know, looking at different directions of K, there are no energy gaps. No band gap exists. Okay, now let's look at that one. What material can this band structure belong to? Well, it's also a metal. And the one you're looking at there right now is copper. And if you see, there is a big difference compared to aluminum, for example. Where? In this lower part. What's the similarity with aluminum? That overall no band gap exists, right? Such as in aluminum. You see, there are band gaps, yes. But overall, if you look at different directions, there are no band gaps. Okay? So at the overall no band gaps. But what's the difference? You see, there are a lot of close, sort of flat parabolas, almost flat parabolas running at low energies. Why is that? Well, that's just with the electron configuration of the material. If you remember, in copper you have 3D bands unfilled, right? If anyone can, or you guys can look at the electronic configuration of copper. You have the 3D level in copper. Well, so that band, those bands are basically attributed to electrons there. That's why you have a lot of energy, sort of a lot of running bands there at low energy values. That's just because of the presence and unfilled of that value, or sorry, that level, the 3D level. in the electronic configuration of copper. Now, look at that. What material do you think the left graph belongs to? Or what kind of material? No? Well, it's a semiconductor. You see a band gap, but the band gap is not huge. Right? You see for different directions as before, right? Different directions. But now you see there's no overlap. Right? Because it's clear that you have no energies allowed here. Well, that's a band gap. Actually, the material you're looking at in the left is silicon. There is a band gap, but it's not huge. In an insulator, that band gap will be quite huge. For example, in diamond is, I think, has 10 electron volts as a band gap, or even more, I don't remember. And if you see, actually, and this happens for all semiconductors, is quite interesting. Always, the bottom of the band gap is at 0 electron volts. So that's how they define it, right? It happens here. Well, this is the gallium arsenide. Okay, this that band structure is for gallium arsenide. It's basically the same as a semiconductor because at the end it is a semiconductor. And you see again, right? The bottom of the band gap is at 0 electron volt. And you can clearly see a band gap, right? And remember, gallium arsenide is sort of the basic for all optoelectronic devices, right? Okay, I guess we can start with the next concept. Let's talk about this last concept of the unit, which is quite interesting and important. What is this Fermi energy? So basically, we've been talking so far about only one electron. And basically that electron was confined to a field of atoms of a solid. We were sort of considering only one electron. And if we think, in general, most of the cases we've been talking about are sort of resemble, most of the cases, not all of them, sort of resemble valence electrons. So that means outer electrons, right? But if we think of a solid, of a material, just think of a 1 centimeter cube material. You'll have 10 to the 22 valence electrons. Valence electrons, just in that material. It will be impossible to describe how all these 10 to the 22 electrons are distributed among the energy levels, right? That will be impossible. Imagine how many energy levels I'm gonna need, and that will be impossible to know exactly how all of these electrons are distributed. I can't know the exact plane, the exact kinetic energy of every single electron. That would be impossible, right? But let's use probabilities. And let's see if we can come up with something sort of understand this concept, right? And more than this concept, understand what's happening with all the electrons and not only with one electron, as we were doing before. What's happening actually with all electrons, right? Well, if you see actually in this electron band diagram, you already saw this, right? Fermi energy. What is this? And it's obviously an important part of any band diagram. And in general, all the properties we're going to talk, magnetic, optical, electric, all those properties are related to the Fermi energy. And where the Fermi energy is, actually the Fermi energy defines these properties of different materials. For now, I'm going to say the Fermi energy is the highest energy that electrons can assume when T equals 0 Kelvin. But that's actually quite confusing. And that might be the concept that you actually, probably if you look for the concept of Fermi energy, that's probably the concept that's going to pop up, right? It's the highest energy that the electrons can assume when the temperature is equal to 0. But that's a bit confusing, so I'm going to redefine that in the next slide. So bear with me. So there are typical values, obviously, for this energy. It actually ranges usually from 2 to 12 electron volts, and you can see just as an example the Fermi energy values for different elements here. You can see the values there, right? So let's say if we sort of do an analogy here, let's imagine that you're filling a cup of water. Sorry, a cup with water, right? So the more water you put, right, you're gonna basically keep filling the cup. So that would basically be sort of Fermi energy if you want to talk about this concept of the highest energy, right? So the higher the Fermi energy, so the more electrons you're putting into that cup, the more water you put, so the higher will be the level of water, the higher will be the Fermi energy, right? But that sort of doesn't make sense, and that's really not clear for most people. So let's actually redefine that in the next slide, but I think actually I'm not gonna have enough time for that. Okay, let's just go to this, I guess. Yeah, and then yeah, okay, I guess I'll have to finish this class in the tutorial anyways. Okay, so if you remember, I'm not sure if when you saw statistics, when you taught statistics, you learned about this equation of Fermi-Dirac statistics. If not, well, you see the equation there. That's an equation that he derived, they derived for probabilities. And in this case, the equation was adapted for the distribution of electrons, and actually what this equation says or describes now is actually the probability that a certain energy level is occupied by electrons. So this equation, that is basically statistics, is just telling me the probability that a certain energy level is occupied by electrons. So I can go to an energy level and say, okay, is this occupied by electrons? Yes, no. Is this occupied by electrons? Yes, no. Okay? So that's basically what this function is describing. It's called the Fermi-Dirac function. I'm not sure if you learned about this in statistics. But if not, well, that's the equation. I'm not going to talk about the derivation or anything because anyways, it was an adaptation, right? Just the original equation, it was adapted now to describe this idea of how electrons are occupying different energy levels, right? So just to make things clear, and because I have to run to the next class, to my other class, what's this? Do you guys know what this term means? I'm sure you've seen it before.
The Boltzmann constant.
Perfect, that's Boltzmann constant. And this temperature, but it's in absolute, it's absolute temperature, right? So it's in Kelvin. And then that's energy, you all know, that's the Fermi energy. And we're gonna talk about what the Fermi energy is. Okay, so let's stop there for now. I'm gonna finish this module on Wednesday. Okay, so there's not gonna be tutorial, or maybe if we have time, we might do something in the tutorial, but there will be a class. So on Wednesday, you have to come to class, right? We have to finish. It's only 12 slides missing, I think 12 or 13 slides more. So we'll finish that on Wednesday. Okay, guys, any questions? Okay, if no questions, that's it, guys. Thank you. Have a good day.
Thank you. Have a good day too.
Thank you, teacher. Goodbye.